My name is Kelly Zoe, and this is my Lab 3 magnetic field of a bar magnet. So the objective is to find how distance affects the magnitude of the magnetic field and also to determine the magnet's magnetic dipole moment. So I used Firefox to show the values of the individual components of the magnetic field, and the procedure was by locating the magnetometer chip in my smartphone, finding the distance from magnet to sensor for various BX magnitudes, found the distance dependence using the logarithmic plot, and then computed the magnetic field at 45 degrees using code and compared it to the measured value found from the experiment. The physics principles used were Biot-Savart law to calculate the magnetic field, magnetic dipoles to find the magnetic dipole moment, and then the distance dependence of magnetic fields. So here's my experiment data. As you can see here, this is the distance in which the x component of the magnetic field was at 20 microteslas. And this is the same for 70, 120, 170, and 220 microteslas. For off-axis field, my d perpendicular was the distance when my net magnetic field had a magnitude of 100 microteslas. These Bx, By measured, and Bz components were found by placing my smartphone sensor d perpendicular distance away from the magnitude in both the x and y direction. The By corrected was by taking the By Earth and subtracting that from the By measured component. And the reason why I subtracted was because both of those components were both positive, so they were both pointing in the same direction. These are the statements that describe what I saw. So when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. As the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. Here are the results. So this is a logarithmic plot found from the Excel file, and to calculate for the distance dependence, as you can see here, the magnetic field of the bar is equal to k r to the n. So if you naturalize both sides, you come up with the equation y equals mx plus b, and from there you're able to see that the n is just the coefficient for the x, so it's negative 2.2378, and that k is 1.106 times 10 to the negative 6. This n makes sense that it's negative because it shows the inverse relationship between the magnitude of the magnetic field and the distance. So as distance increases, the magnetic field would decrease. Also trying to find the dipole, the magnetic moment, I set k r to the n to the Biot-Savart law. However, here the component, the r to the third, thus 3 would be replaced with the magnitude of n. I found the magnetic moment to be 5.53 amps meters squared. So this is the code. So place the magnetic moment magnitude in line 16, created a function for my magnetic field from lines 24 to 28, and then created my observation location. So 2 were on axis, so they were on the x-axis, both in positive and negative directions, and the 4 perpendicular to the axis were for the the y and z component, both in the positive and negative direction. So here, in each of these groups, they were to calculate the r vector, which was the observation location minus the source location, calculate the magnetic field using that locations, and using the dipole B function I created above, and then created the arrow where the axis had the magnetic field with multiplied by the scalar factor. And this was the same for both the on-axis and for the perpendicular axis magnetic field arrows. So over here was to find the magnetic field at 45 degrees from the axis. So as you can see, my r vector was the observation location minus the magnet's original position, and then calculated my magnetic field with the dipole B function, and then created that arrow to show the magnetic field in the output. Here was my output. As you can see, the 2 orange arrows show the magnetic field on axis, the cyan arrows show the magnetic field perpendicular to the axis, and the green arrow is showing the magnetic field 45 degrees from the axis. Here's my measured and calculated magnetic fields. My measured B was negative 2.88 times 10 to the negative 5, 9.46 times 10 to the negative 6, and negative 5.18 times 10 to the negative 5 teslas. My calculated B from the code was 1.011 times 10 to the negative 5, 3.034 times 10 to the negative 5, and then 0 teslas. These were measured at a distance of 0.234 meters. So what if you hadn't oriented your experiment to compensate for the magnetic north and had instead laid out your meter stick at some intermediate angle with respect to the Earth's magnetic field, how would your results have changed? I said that the results would have been less accurate because the measurements were interfered by the magnetic north, and that means that the n, mu, and k values would change. What if you were to stick two identical magnets together end to end and run the experiment again? How would you expect your measurements to differ? I would expect my measurements to differ with the magnitude of the magnetic field being greater than what it was originally.